Okay, I'm going to call this because we have some people done and some people still trying to figure out what's going on. So I want to go over this now because this one was different. We had not done anything exactly like this. So when you look at this, you have to think about what's going on in my beaker. Now, this is done the same way as the previous problem, but what's in solution is your base B and your BH+. So if we add hydroxide, it's going to react with the BH+, the protonated base, or the conjugate acid of the weak base, and it's going to make base plus water. So we're using up BH+, and we're making the base. So if we look at what we have in here, I decided we've got the morphine, morphinium chloride. So these are the formulas for morphine and morphinium chloride. We know the pKb for morphine. So the POH is pKb plus the log of BH plus over B. So that's 6.13 plus the log of the salt concentration, 0.750 molar, divided by the base, 0.5. So when we divide, we get 1.50. So the POH is 6.13 plus 0.176 is 6.31. The pH is 7.69. So we've figured out the pH of our basic buffer. Now we have to think about what happens after I add the strong base. The base concentration is 0.5 moles per liter, and I'm adding this to 1 liter of buffer, so I have 0.5 moles of base in my beaker. For my protonated base, or my conjugate acid of that base, it's 0.75 moles per liter, so I have 0.750 moles of the protonated base, or the conjugate acid, in that beaker. Now we'll think about how much hydroxide I'm adding. I have 10 milliliters of sodium hydroxide is 1 mole per liter, and so I'm adding 0.0100 moles of hydroxide. That's equal to the moles of the BH plus used up, which is equal to the moles of the base made. So now I started off with 0.5 moles of base. I made more from the sodium hydroxide, so I now have 0.510 moles. I started off with 0.750 moles of the BH plus. I used up 0.01 moles, so I have 0.740 moles left. So now I can plug these moles back in because the mole to mole ratio is the same as the molar to molar ratio. So my POH is 6.13 plus the log of 0.740 over 0.510. So that's 6.13 plus the log of 1.45. So that is 0.16. So the POH is equal to 6.29. Then we can find the pH from pKw. 14 minus 6.29 gives us a pH of 7.71. So again, we added a fairly large amount of sodium hydroxide, and the pH only shifted by 0.02 pH units. So this buffer is doing a good job. And that's how we look at buffer problems. Now, there's a lot of chemistry going on, and in order to be successful when we get to the test, you need to understand exactly what's in the beaker in terms of acid-base conjugates and what happens when I dump in strong acid or strong base. Strong acid will react with the conjugate base. It'll use up conjugate base and make the conjugate acid. Strong base will react with the conjugate acid, use up conjugate acid, and make more of the conjugate base. And it doesn't matter whether it's an acid or a base buffer. It just matters that you look at the conjugate pairs correctly. So I know this is kind of messy and complicated, which is why it's going to take a lot of time out of class to sort this out. You have to practice this. Most of you will not be successful if you tried to take the test after just looking at my example. Okay? All right, do you have any questions? So, we've looked at acids. We know how to calculate the pH of acids. We've looked at bases. We know how to calculate the pH of bases. Now we're going to try and figure out how to calculate the pH during a titration. In a titration, we are mixing acid and base. At the end of the titration, we've made water and a salt. Some of those salts have no pH effect, so the pH will be neutral, the same as water at the end. Some salts contain conjugate bases of weak acids or conjugate acids of weak bases, so they will have a pH effect. When you have a strong acid, strong base titration, you're completely using up whatever you add and just making water and a salt that has no pH effect. But when you have strong weak combinations, you're making salts that are conjugates of weak acids or weak bases, so you actually have made the conjugate and you have a buffer partway through the titration. So titrations get really messy. Like this was a little messy. Titrations get really messy, and now we're going to take a look at those. So when we deal with a titration, that is a reaction in solution. We've been doing lots of them. You're getting to be titrating experts in lab. We talk about the equivalence point. The equivalence point is where we have the stoichiometric equivalent amounts of acid and base so that everything is neutralized. Then we talk about the end point. Now, in an ideal world, the end point where we stop titrating would be the equivalence point. Sometimes we don't stop exactly at the equivalence point because we stop when our indicator changes color. So when we think about a titration, they have 4 different zones. Typically, we look at titrating where we have an acid in the beaker and we're adding a base. And so we're looking at the volume of the base that's being added. That's increasing on the x-axis, and the pH is increasing on the y-axis. And most of the time, we'll have titrations curves that look like this. We start at a low pH, and as we add base, the pH goes up a little bit, but not very significantly for a while. Then all of a sudden, it shoots right up, and then it sort of levels off again. And right here, where we have this change in inflection of the curve, this is the equivalence point. Now, pH is increasing, and here all of a sudden the pH goes way up. So now when we look at this, if we're looking at volumes, from this point to this point where the pH kind of levels off, this is usually about 1 to 2 drops of titrant. So can you see that if the pH at the equivalence point is here, but our indicator changed color here, it would probably be okay because it's less than 1 drop difference in the pH. So that's why we can sometimes get away with using phenolphthalein as an indicator. It actually changes color about pH of 9. And we might be looking for something whose endpoint is about pH of 7, but it's within of like a third of a drop. So it works just fine. So when we're talking about titrations, we have 4 different zones where we can deal with the pH. The first zone is right here, where all we have is acid in a beaker or an Erlenmeyer. And we can calculate the pH of the acid before our titration begins. Then we have the next area in our titration curve, which is here, before the equivalence point. I've added some base, but I'm not done titrating. Once we reach the equivalence point, this is zone 3, we can calculate the pH at the equivalence point. And then up here is where we keep going. We keep dumping in base after we're done titrating the acid, and that's zone 4 after the equivalence point. This after the equivalence point, that's where you get that pink with the phenolphthalein when you've dumped in extra hydroxide. So the acids and bases can be strong or weak, and the calculations are different for each situation. Each situation is pretty much a rehash of something we've already done, but you have to really think about where you are in the titration and what you're trying to calculate. So as you start to move forward with these, we have to sort of come up with a thought process for how to